After studying this module, you shall be able to know about configurational equilibrium as a model for anomalous magnetic moment, learn about anomalous magnetic moment arise in magnetically concentrated complex, identify two types of magnetic exchange coupling, first ferromagnetism and second antiferromagnetism. Identify physical origin of ferromagnetism and magnetic domains. Evaluate mean field theory of ferromagnetism. Learn about magnetic sublattice and ferrimagnetism.
Configurational equilibrium. As we have already discussed in the previous module that N-aryl substituted salicylyl diamine nickel 2 complexes show anomalous magnetic moment. The magnetic and spectral measurements on these complexes in xylene or bibenzyl solution suggest that the presence of tetrahedral species along with the associated 6 coordinate species. Therefore, three forms of N-aryl complexes coexist in the solution, that are associated planar, diamagnetic and tetrahedral. So there is an equilibrium between the diamagnetic planar and paramagnetic tetrahedral molecules. It is important to recognize that planar and tetrahedral molecules have the same coordination number. So the diamagnetic planar paramagnetic tetrahedral equilibrium is called configurational equilibrium. The planar tetrahedral equilibrium is also observed in the nickel chelates of aminotropone iminates. The magnetic susceptibility and electronic spectra are dependent on temperature, solvent and nature of N substituent. The paramagnetic species in solution is tetrahedral, not octahedral. This fact has been established by evidences from several sources. First, the complexes are monomeric in solution. Second, the magnetic susceptibility increase with an increase in temperature, and there is no correlation exist between the position of equilibrium and expected coordinating power of the solvent. These evidences ruled out the presence of solvent-solute and solute-solute interaction in the similar complex. The planar tetrahedral equilibrium is pressure dependent. The planar form is favored at high pressures, suggesting a smaller partial molar volume than for the tetrahedral form. Further, there was no indication of the transformation to a coordination number greater than 4 with increasing pressure. The variation in behavior with change in the R group can be fairly satisfactorily accounted for on steric grounds. Clearly, as the R groups become bulky, steric repulsions between them are expected to become important in a planar structure. Rotation of the planes of the chelate rings towards a tetrahedral configuration for the central nickel atom should relieve the steric strain. It is predicted, therefore, that the equilibrium should shift in favor of the tetrahedral form as the size of R increased. This proved to be the case as shown in table on the screen. Extensive diamagnetism of the N-aryl substituted complexes is attributed to a rotation of the plane of aryl ring out of the plane of seven-membered ring. We have already discussed in the previous module that N-methyl and most N-aryl salicylyl diamine complexes of nickel show paramagnetism mainly due to molecular association. However, the paramagnetism of branched N-alkyl substituted complexes is predominantly due to the presence of tetrahedral species. The effect of branching of an alkyl substituent is reflected in the solid state as well as thus the N-propyl compounds, for example, are planar even when substituents are present in the 3 position of salicylyl diamine ring. The tertiary butyl chelates on the other hand are all pseudo tetrahedral. Both stereochemistries are found for the solid S-alkyl complexes. The choice of configuration in these cases depend on the nature and position of the ring substituent. In inert solvents, at room temperature, the N-propyl derivatives are predominantly planar. Tertiary butyl derivatives largely pseudo-tetrahedral and S-alkyl chelates coexist in comparable proportion of both forms. Assignment of the stereochemistry in the solid state was made on the basis of magnetic moments and reflectance spectra, and in solution on the basis of dipole moment and molecular weight evidence. Although there is evidence for some association in solution of the alkyl derivatives, it has been shown that at or above 37 degrees Celsius, they are essentially monomeric under the same conditions of the solvent, concentration and temperature, where they were found to be appreciably paramagnetic. Dipole moment of some N-alkyl salicylate diamine nickel chelates are shown here on the table, which are recorded in the solvent benzene. Magnetic exchange coupling. As we have already discussed that the anomalous magnetic moment is the magnetic moment for a metal ion in a discrete molecular species, having a value which falls outside the range of the values predicted from considerations of the spin and orbital angular momentum in the ligand fields of the given strength and symmetry. The discrete molecular species means that there is no secondary magnetic interaction between the neighboring molecules. In other words, for these systems, any ferromagnetic or antiferromagnetic interactions are lacking. It explains these are magnetically dilute. For such systems, magnetic property of a metal ion is influenced only by the ligand field. Anomalous magnetic moment may also arise in magnetically concentrated systems. The magnetic interaction in such a complex occur when the neighboring centers are close enough for direct or indirect orbital overlap. This interaction affects the magnetic property of the complex and swamps the ligand field effect. In fact, almost all paramagnetic complexes to a certain extent are involved in exchange interaction, which is dominant only at low temperatures. When the exchange interaction energy is greater than kT, the result is a cooperative phenomena of ferromagnetism or antiferromagnetism. The magnetic moment of a complex involved in an exchange interaction may be more than or less than that of a complex not involved in the exchange interaction. The former situation is a characteristic of a ferromagnetic substance, whereas the latter is a feature of an antiferromagnetic substance. So there are two types of magnetic exchange coupling. First is ferromagnetism and second is antiferromagnetism. For ferromagnetic substances, the neighboring spins align parallel to one another below a certain critical temperature. That temperature is called Curie temperature, and below this Curie temperature, the material remains permanently spin aligned even when the field is removed. It is a field dependent effect. In an antiferromagnetic substance, the neighboring magnetic centers are opposed to each other, but in ferromagnetic substance they are aligned parallel. For antiferromagnetic substances, the neighboring spins align antiparallel with one another below a certain critical temperature that is known as Néel temperature, and below Néel temperature the material tends to remain spin aligned and has a lower moment than expected. The coupling forces are responsible for the alignment of the magnetic spins. The spontaneous alignment of magnetic dipoles in ferro or antiferromagnetic states needs some positive energy of interaction between neighboring spins. The origin of this coupling is quantum mechanical. Physical origin of ferromagnetism. The alignment of spins in a ferromagnet is parallel. This is because of the presence of an strong internal magnetic field known as the molecular field. Thus, ferromagnetism is an ordered state and external field is not necessary to achieve this state. The effect of a ferromagnetic or an antiferromagnetic interaction is observed over a large distance in a substance, and such an interaction is known as long range order. This interaction is important for only the first four nearest neighbors. The property of ferromagnetism is due to the direct influence of two effects from quantum mechanics, that are spin and the Pauli principle. The intrinsic spin angular momentum of an electron has a magnetic dipole moment associated with it and creates a magnetic dipole field. In many materials, the electrons come in a pair of opposite spin which cancel one another's dipole moment. Only atoms with unpaired electrons can experience a net magnetic moment from spin. A ferromagnetic material has many such electrons, and if they are aligned, they create a measurable macroscopic field. The spins or dipoles tend to align parallel to an external magnetic field, an effect called paramagnetism. Ferromagnetism involved an additional phenomena. However, the spins tend to align spontaneously without any applied field. This is purely quantum mechanical effect. According to classical electromagnetism, two nearby magnetic dipoles will tend to align in opposite direction. In a ferromagnetic, however, they tend to align in a same direction because of the Pauli principle. Two electrons with the same spin cannot lie at the same position and thus feel an effective additional repulsion that lowers their electrostatic energy. This difference in energy is called the exchange energy and induces nearby electrons to align. Magnetic domains. A ferromagnetic substance is considered to be composed of a number of small regions called magnetic domains. At long distances, the exchange energy advantage is overtaken by the classical tendency of dipoles to anti-align. This is why in non-magnetized ferromagnetic material, the spins in whole material are not aligned. Rather, they are organized into domains that are aligned at short range, but at the long range, adjacent domains are anti-aligned. The transition between two domains where magnetization flips is called a block wall and is a gradual transition on atomic scale, that is covering a distance of about 300 ions for iron. Thus, an ordinary piece of iron generally has little or no net magnetic moment. However, if it is placed in a strong enough external magnetic field, the domains will reorient in parallel with that field and will remain reoriented when the field is turned off, thus creating a permanent magnet. This magnetization as a function of the external field is described by a hysteresis curve. Although this state of aligned domains is not a minimal energy configuration, it is extremely stable and has been observed to persist for millions of years in seafloor magnetite aligned by the Earth's magnetic field. The net magnetization can be destroyed by heating and then cooling the material without an external field. However, as the temperature increases, thermal oscillation or entropy competes with the ferromagnetic tendency for spins to align. When the temperature rises beyond a certain point, called the Curie temperature, there is a second order phase transition and system can no longer maintain a spontaneous magnetization, although it still responds paramagnetically to an external field. Below that temperature, there is a spontaneous symmetry breaking and random domains form, which is in absence of an external field. The Curie temperature itself is a critical point where the magnetic susceptibility is theoretically infinite, and although there is no net magnetization, domain like spin correlations fluctuate at all length scales. Mean field theory of ferromagnetism. Consider a paramagnet with a concentration of n ions of spin s. Given an internal interaction tending to line up the magnetic moments parallel to each other, we shall have a ferromagnet. Let us postulate such an interaction and call it the exchange energy. The orienting effect of the exchange field is opposed by thermal agitation, and at elevated temperatures, the spin order is destroyed. We treat the exchange energy as equivalent to the magnetic field Be. The magnitude of the exchange field may be as high as 107 Gauss. We assume that Be is proportional to the magnetization. The magnetization is defined as magnetic moment per unit volume unless otherwise specified. It is understood to be the value in thermal equilibrium at the temperature T. If domains are present, the magnetization refers to the value within a domain. In the mean field approximation, we assume each magnetic atom experiences a field proportional to the magnetization. Thus, Be is equals to lambda m, where lambda is the constant independent of temperature. The Curie temperature Tc is the temperature above which the spontaneous magnetization vanishes. It separates the disordered magnetic phase at T is greater than Tc from the ordered ferromagnetic phase at T is lower than Tc. Consider the paramagnetic phase. An applied field Ba will cause a finite magnetization, and this in turn will cause a finite exchange field Be. If chi p is the paramagnetic susceptibility, then M is equals to chi p into Ba plus Be in CGS units, and in SI units it will be M is equals to mu naught chi p into Ba plus Be. The magnetization is equal to a constant susceptibility times a field only if the fractional alignment is small. As we know that the paramagnetic susceptibility is given by the Curie law, that is chi p is equals to C upon T, where C is the Curie constant. Substitute the value of chi and Be in the equation number 1, we get M is equals to chi p into Ba plus Be. M is equals to C upon T into Ba plus lambda M. On rearranging equation number 2, it becomes M upon Ba is equals to C upon T minus C lambda, and we know that chi is equals to M upon Ba. Putting equation number 3 in 4, we get chi is equals to C upon T minus C lambda, and that becomes chi is equals to C upon T minus Tc, where Tc is equals to C lambda. Equation number 4 is the mathematical form of Curie-West law from quantum theory of paramagnetism. The Van Vleck equation for the large multiplet width is shown on the screen, where J is the total angular momentum quantum number and Curie constant. Then C becomes is equals to Nj into J plus 1 G square beta square upon 3k. From equation number 4 and 5, we may determine the value of the mean field constant lambda. Lambda is equals to Tc upon C, that is equals to 3kTc divided by Nj into J plus 1 G square beta square. For iron, Tc is equals to 1043 Kelvin, G is equals to 2, and J is equals to S is equals to 1, as iron is 3d8 system. N is equals to 10 raised to power 23 centimeter inverse. Putting these values in the equation, we get lambda is equals to 7300. With M is equals to 1700, we have Be is equals to 10 raised to power 7 Gauss, that is equals to 10 raised to power 3 Tesla. The exchange field in iron is very much stronger than real magnetic field due to other magnetic ions in the crystal. A magnetic ion produces a field at its neighbor that is equals to mu b divided by A3 is equals to 10 raised to power 3 Gauss or zero point 0.1 Tesla. Now taking all the possible energy levels and using temperature independent paramagnetism term N alpha, magnetic susceptibility of a dimer becomes chi is equals to 2n g square beta square upon kt into 1 upon 3 plus exponential raised to power minus 2j upon kt plus n alpha. The magnetic susceptibility per gram atom of the interacting ions will be half of the first term plus n alpha. Therefore, chi A is given by the equation shown on the screen. Now, equation number 7 is known as Blaney-Bowers equation. Rearranging equation number 7 and taking log, we have minus 2j is equals to kt into 2.303 log into n g square beta square upon kt chi a minus n alpha minus 3. Magnetic sublattice and ferrimagnetism. A substance can be divided into two or smaller lattices, and each sublattice possesses uniform magnetization. Let us consider two sublattices A and B which interact with each other. The corresponding magnetizations are represented by Ma and Mb. When Ma and Mb are equal to each other, the substance is antiferromagnetic. When Ma is not equals to Mb, the substance is ferromagnetic. It explains the magnetic moments associated with the two sublattices are not equal. The resultant magnetization is then M is equals to Ma plus Mb. The molecular field constant MAB in a ferrimagnetic compound is much larger than the antiferromagnetic molecular field constant, that is MAA or MBB. The spontaneous antiparallel alignment occurs also in ferromagnetic substances at the transition temperature. But since the non-equivalent sublattices in it cannot balance each other, it retains a small permanent magnetic moment. Ferromagnetism requires free electrons in the conduction band. Ferromagnetism occurs only in metals. However, ferri and antiferromagnetism can also occur in insulators such as metal oxides. Magnetic susceptibility of ferrimagnets. Let us consider separate Curie constants Ca and Cb for the ions on the A and B sublattices. For simplicity, let all interactions be zero except for an antiparallel interaction between the A and B sublattices. Ba is equals to minus mu Mb, B is equals to minus mu Ma, where mu is positive. According to the mean field approximation, MAT is equals to Ca into Ba minus mu B, and MBT is equals to Cb into Ba minus mu Ma, where Ba is applied field. On solving equation 8a and 8b for Ma and Mb to obtain the susceptibility at temperature greater than Tc, we get chi is equals to Ma plus Mb upon Ba, that is equals to Ca plus Cb into T minus 2 mu Ca Cb divided by T square minus Tc square. Ferrimagnetism in magnetite. The ferrimagnetism has been observed in magnetite. Magnetite is an inverse spinel and exhibits two lattices, that is 1:1 mixture of Fe2 plus and Fe3 plus ions in the octahedral structure, Fe3 plus in the tetrahedral structure. The octahedral sites and the tetrahedral sites are aligned in the different directions. The ferromagnetic alignment of the octahedral sites is necessary for delocalized carrier transport of the minority spin T2g electron. This mechanism is called double exchange. The double exchange mechanism is a type of a magnetic exchange that may arise between ions in different oxidation state. This theory predicts relative ease with which an electron may be exchanged between two species and has important implication for whether material are ferromagnetic, antiferromagnetic or neither. The double exchange predicts that this electron movement from one species to another will be facilitated more easily in the electrons do not have to change spin direction in order to confirm the Hund's rule. When on the accepting species, the electron hopping to the neighboring ion is favored if neighboring ions are ferromagnetically aligned, and not favored if neighboring ions are antiferromagnetically aligned. The ability to hop reduces the kinetic energy, hence the overall energy saving can lead to ferromagnetic alignment of the neighboring ions. Double exchange results in ferromagnetic exchange coupling. The transfer of an upspin electron would leave the ion from which the electron is transferred. In a higher energy state, which is shown on the screen, electron transferred must have opposite spin to those of the receiving ion, that is from Pauli's principle. For magnetite, experimental values of 1 upon chi versus T are plotted. The curvature in the plot is a characteristic feature of a ferrimagnet. Below the antiferromagnetic limit, Ca is equals to Cb.
Summary. In this module, we discussed that configurational equilibrium can also give rise to anomalous magnetic moments. For example, equilibrium between diamagnetic planar molecules and paramagnetic tetrahedral molecules with same coordination number of metal ion is called configurational equilibrium. In magnetically concentrated complex, anomalous magnetic moment may arise due to magnetic interaction in the neighboring centers. There can be two types of magnetic exchange coupling, one ferromagnetism and two antiferromagnetism. In ferromagnets, the alignment of spin is parallel. However, the alignment of spin is antiparallel in antiferromagnet.